Okay, here we are. Welcome everybody. Welcome in Alkemy. Thanks for the people that are here with us. Carry the hot summer days, the huge strides, very appreciated. And thanks to the people that is joining us today. First of all, I want to thank also the friends that Data Science Milan organized this meeting. Friends that are here, they will be connected. They are connected
In a few minutes.
And also thanks to Federica and the marketing people, HR, and people from Alkemy that are setting up this game to us. Okay, so my name is Marcello. I'm a senior data scientist in Alkemy, and I will introduce this event, which is the first event in Alkemy that we also together with the data science. It's also the first AI dinner and international series of events that take place all over Europe and for the first time in India. So it's always a joy to meet people from our field to discuss ideas and to build net. So I will briefly introduce who Alkemy is, who we are, what do we do. So Alkemy is an international public company which offers solutions to improve the market position and competitiveness of large and medium-sized companies. How? Driving the evolution through data, technology, and creativity. Alkemy was born 10 years ago, 32 people. In 10 years, we are now way more than 800. This is not up to date chart. We are building this. We are growing this fast. Two acquisitions and in different locations. What we try to do is to build a composition of different competence, different skills. Consulting, data analytics, digital marketing, technology, trends, from the speakers. Very different amounts of money for each other.
Intervention. Okay. So a lot of different skill trying to, and consulting, of course, a lot of different skill trying to help in any way our clients to evolve their businesses. So today I represent data and analytics. I am a senior data scientist at Alkemy. We have a competence center about data analytics, around 120 people, a little bit more than that, again, not up to date. What we do is what is today called data science. Alkemy bought a company that was called Nunatak that started operation in 1994. 1994, it was not called data science, it was called some other thing, statistics, BI, and it evolved. So some of the people that are here with us, not now, but in Alkemy, extremely very experienced people and pioneer in some sense. Okay. More than that, me and Davide, that will hold the talk in a few minutes. We've been asked to lead this internal department. We call it Deep Learning and Big Data department, with the mission to try to help Alkemy to evolve their positioning, their offers, and the way we do data science projects. It consists in three areas: R&D, infrastructure, education. These are the main pillars. Focus on POC and data products. New domains, try to expand what we do. Continuous training, because it's the most relevant part, people, and we have to evolve them to evolve the business of our clients. Very fast, we operate on very different domains, large companies, interesting challenges. Every day is different. So we try to be up to these challenges every day, and we believe that networking with people in our same domain can help us to strengthen our position and to be relevant in this business. Okay. Today we are here with our friends from Data Science Milano, AI Guild, that will introduce itself very quickly. And last thing that I say is, today we will talk about robustness in AI, a very relevant topic nowadays, and every day is more important to focus on these kind of things. Davide, which is a lead data scientist here with us and helped me co-leading the department that I introduced, will provide us with a super interesting talk that I hope will start conversation and the Q&A after that. Now I let Paolo to take the stage.
And Daniel also joins.
Daniel also joins, so welcome, Daniel. In a few minutes will be up to you. So thank you again, welcome, and now I leave to Paolo the stage.
Yeah. So where are the slides? Here. Okay. Okay, so hello. Let me see. Okay, perfect. So hello, everyone. I'm very glad to see you, all of you, in presence, and as well also welcome also to all of those people who are watching us using our YouTube channel. Okay, so just a very brief introduction on what is Data Science Milan, what is our community. So we are an independent group founded in 2016. We are more than 2,000 members, and we organize once a month physically and online events. The agenda is pretty the same all the time, which is a tech talk, Q&A, and then aperitivo. And the aim of Data Science Milan is two are the aims, actually. The first one is to spread data science culture in Italy, in Milan, in all the Italian organizations. And the second one is to promote events so that we can create networking occasion, okay? So to meet real data practitioners in presence, okay? This is the staff. So this is are the people that are behind the organization. And I'm really glad also that I have this occasion to announce that we have 3 new volunteers. So I think that I talk for the staff people when I say that I'm really glad that Leonardo, Matteo, and Fabio joined the crew in the last month. So thank you guys to join the crew. But at the same time, if some of you would like to join our staff, we are really happy to give you a warm welcome. Just 2 slides about our so what are our channel and our resources. So all of our events are recorded, and so you can find on our YouTube channel the recordings. And as well, the slide, you can find the slide presentation in our LinkedIn SlideShare. We have a blog Medium where you can find the summary of each event in which you participate. A Slack channel for 24/7 communication, job posts, and just to keep in touch with Slack. And of course, we have all these kind of social network. So if you want to spread the word, just tag us, give a like. And of course, if someone of you would like to, is interested to do a talk, just send us an email or let's keep in touch during the event. And I think that's all. Enjoy the talk, the event, and thank you so much.
First, we have also Dania from. Oops. Dania, just one moment. I need to do this. It's easier. Okay. Dania, if you want to introduce yourself and AI Guild, of course.
Yes, let me share my window.
Okay. Not.
Yes. Can you see my presentation?
Dania, just for a moment, we don't hear you. But I don't know why. Okay.
Yes, do you hear me?
Okay.
Yes.
Now we can hear. Sorry.
And you can also see my presentation, right?
We could hear you.
No, not anymore. Okay.
Why?
Maybe it's on my side.
Any ideas, guys?
Does this change anything for you?
Dania, we don't hear you. I don't know why. No.
Okay.
A moment.
Okay.
Non so, qualcuno mi deve dare una mano.
Lo riavviamo e di provare a ricollegarsi. Un secondo abbiamo sentito.
Sì. Il problema è che non riesco manco a...
Hi. Do you hear me now?
Per un attimo si sentiva, sì, però...
Non so che
Dania, you can hear us, right?
Yes, yes, I hear you well.
I don't hear you, and let me check why. Just one moment.
Okay.
Maybe. Okay. Can you try now?
Yes, do you hear me?
Yeah, thank you.
Cool.
Sorry.
Okay, not a problem at all. Thank you, first of all, for the opportunity to present remotely. I wish I could be there with you, but I am in Berlin now. And yes, I have some slides for you. Let me try to share again. Let me know when you see it, please.
Yes, we see you, Daniel.
Cool. Cool. So thank you for joining today. We are very happy that we are doing our first AI Guild dinner in Italy together with Alkemy and Data Science Milan. So I'm very excited about this new collaboration with you. I'm here to introduce the AI Guild. We are currently more than 1,600 specialists fluent in data. So we have different roles and people working in the different industries all over the globe that are part of the AI Guild. A little bit about me. So I started the AI Guild, so I'm one of the founding members, and now I work full-time as a director data lift, which is our yearly event in person. This was just a month ago in Berlin, and we are doing it every year again. I am working in data since 2012, so 10 years now, and I'm happy to connect with you on LinkedIn, so please reach out. It's always nice to get to know more practitioners. The AI Guild has two main initiatives. The one is Data Lift. So this is what I mentioned, our yearly event. This is about use cases in production. So the AI Guild organizes the event where members can present their use cases, and I have been doing the event since 2019. So now I have done over 50 assessments of different use cases. And from that, we also support companies that want to understand how they can scale their infrastructure to deploy use cases if they haven't already, or deploy more use cases. And then after recommendations, we also work with companies together with the implementation, deployment, and monitoring of their use cases. The other initiative that we have is the data careers. So here we work together with the professionals and the companies to establish the roles and also to understand what a career path looks like. So we work with experts and leaders which are more than 10 years in the field to do accreditation to set the quality standards for the profession. For seniors and leads, we do competency profile and team certifications. And for entry-level professionals, we have the academy. So this is a few of our clients that are working with us in either data lift on deploying use cases or data career to establish roles and career development. And so if you would like to join us, so this is a picture of me and some of our members that met last month at the Data Lift team. We are, more than half of us are in the DACH region, so that's why now it's an expansion to Italy. So if you would like to become part of our community, we're happy to extend it and get more exchanges with you. And yes, so we are always looking to have more local events, but also then to do the yearly get together at the Data Lift. So here's my invitation for you to join our community. You can check the website, theguild.ai, and the membership is for free. So once you apply, you get in our LinkedIn group and you have access to all the members, to opportunities to be a speaker, and also to host other dinners together with your companies or together with your colleagues there in Milan again. Thank you.
Thank you, Daniel. Thank you. That was nice. Just one moment, I will try to bring this desktop, this Windows back on my. Okay. Nice. Now I share my screen once again. It's really hard. Okay. Okay, if you confirm me that you are seeing the screen, I think we can start. And first, Dania, I wanted to thank you also for your leader presentation. Also, I want to sponsorship the Data Lift Summit that we had in Berlin like 1 month ago. It was really a nice experience. We were there together, myself with Marcello and other people of the Deep Learning and Big Data department. It was a really nice experience. So I recommend you check it out for the next year. But now let's jump into the topic because we had many different people presenting themselves. Now let's talk about data science. Tonight, I'm really glad I can deliver some ideas about this topic that is already many years I'm thinking about. And I'm glad I'm seeing kind of increasing attention in the industry as well, not only in academia. Disclaimer, I'm from academia, I'm from the industry, but in 1 second I talk about myself. So this is me, seems so. And my name is Davide. I study statistics, as probably many of you here. It's already a bit of time now that I'm working with data, but not just data. It's more about, I like thinking that what I'm doing is to answer questions using data. That is probably a good definition of being a data scientist. I'm working as a freelancer data scientist, and I also do some teaching every now and then about machine learning, but I didn't mention it here, but I'm also doing some mentoring, often on a free basis, so for free. And I really find this as a very nice experience, and I encourage everyone to do the same. And currently, what I do for a living is helping Alkemy, together with Marcello, to build this, we already mentioned it many times, deep learning and big data department, where we are trying to focus on ideas like this one we will talk about tonight, and to bring them into reality, somehow productionizing them, or at least having some concrete blueprint of those ideas. I'm really happy to connect with all of you, and also to work together on ideas or projects, also on side projects. So let's try to get in touch. I think I already did with some of you tonight. And tonight, just a last mention about the event we are having now. I intentionally took both the pictures you found maybe online. There is even a third one from the Data Science Milano meetup, but I didn't have space. Don't take it personally. So from Alkemy, from AI Guild, but also here mentioned Data Science Milano, I want to thank all of these people that made this possible, and I really hope it's only the first time we do this. But let's start. So I want to start from the simplest possible case ever that we can think about in deep learning. And for the ones of you that are here and don't know about technical stuff, I see some of you, try anyway to follow, don't focus too much on technicalities. I think it's fun, the topic anyway. So, but what is the MNIST data set? Is this a very common data set of digits that until some decades ago, the idea of taking these pictures and translating them into some actual numbers looked like an impossible challenge that is currently solved like that really easily through a super simple neural network. In this case, one of the many architectures you could use to solve this problem, and I want to repeat, going from the picture to the prediction of the digit, one of these architecture is the LeNet, that is a convolutional neural network, really straightforward. So you could think, why am I starting from such an easy topic? Or where am I going? What's my point? My point starts from the following question. What happens if we do something a bit weird with this neural network? If we take a picture that is, of course, not related with digits at all, and we give it to the neural network, what's going to happen, just as an experiment? And you can do that really easily. Of course, you take the picture, you downscale it as a digit, you have exactly the same shape of the shape you are expecting for a LeNet network, and you give it to the network. What we would expect in an ideal world, in an ideal setting, is something like that. Potentially, ideally, a uniform distribution of the multi-class classification problem that we are trying to solve, that we would interpret as well, I have no idea what to do with this image. It's not my domain. I don't want to process it. I don't know which number this could be. But what do we get instead? Maybe someone of you even found already this happening in real life. What we get, and you can test it, is instead the following result. we get an extremely strong prediction, strong in terms of probability, that this chicken is actually a 6. So our perfect, extremely powerful neural network, the LeNet, that is the de facto standard to solve this MNIST problem, doesn't see absolutely in any possible way that the chicken is not a digit. Actually, the other way around. It's telling us the chicken is a digit, is a 6, and I'm very, very confident about it. Now, if for the people of you that are familiar with statistics or that study statistics, we usually have a set of metrics or KPIs that we give together with the estimates, namely the p-value or the confidence interval, and other kind of contextual information that are telling us, can I actually trust that this is a good estimate or a good prediction, or is just noise? With at least the native architecture or the basic architecture of deep learning, and in general with more complex models coming from machine learning, we don't have, at least if we don't do anything, this kind of contextual safety metrics. So if we only check the probability of the discrete distributions we are trying to approximate, we could be misled. And this happens even if we do something a bit more complex with the same network. If we take the another similar MNIST dataset, the fashion MNIST dataset, that contains tiny images of clothes, and we give them to the LNet network, we have, once again, really confident predictions. For example, almost the 90% of these examples are classified as digits, that of course are not digits, with a probability that is greater than the 70%. That is, once again, we are saying for all of those pictures that are not digits, and we can agree on that, even if some of them maybe look like a 1, but still, we are super confident that we are classifying digits. So I made this example intentionally, and I hope you can follow me. I'm not saying that this is a real life example, but to focus on a narrow specific domain, we need to simplify something. So I intentionally simplified on the data. Let's now, in this simplifying context, try to find a solution. The solution to this problem is what we call robustness matrix. And this is the object of tonight, or the actual topic that I want to talk about with you. The questions that we are having now in our mind is if we can actually trust deep learning predictions or not. If a so easy problem, like MNIST problem is the easiest we can think about, can present such a super weird behavior. Can we trust deep learning, especially if we go to more sensitive and really crucial areas like healthcare or manufacturing or autonomous driving? In the context where risks must be controlled, and I will come back to risks in a moment because this is really important. Sometimes no prediction, avoiding a prediction, is a better decision than what we did before. So we would like to have some kind of metrics that can work like in this pseudocode. If I don't reach the threshold, I just raise an exception. I don't trust the prediction. And I stop there. In a moment, I will say more about other approaches for robustness that don't involve avoiding the prediction. But tonight, I want to focus on avoiding the prediction. We could try to fix the prediction or fix the model. And I'm not discussing about this tonight because it's even more complex. So if we agree that something like that could be a feasible option to solve our problem. The next question is how a robustness matrix should look like. Well, it should work like telling us that you are risking too much and you shouldn't be confident in your prediction. It should be, of course, computable with no labels, because otherwise it's too easy. So we don't know the truth. We don't know the ground truth, of course. But more interesting, should work in a kind of real-time setting. So if there is a stream of inputs, I should be able to process them one after the other one with no, and this should be feasible also from a technical perspective. Ideally, it should be easy to plug in into already working and existing machine learning pipelines without the need of reinventing the wheel and building all the models from scratch. And should also have a good combination of low false positive rate and low false negative rate, namely should be effective in detecting the chickens, so as many chickens as possible. But it should be also, it shouldn't classify everything as a chicken, just to be sure, you know. So we don't want to discard too many good predictions, and this is the low false positive rate, and the low false negative rate from the other side. So it doesn't look like an easy challenge. And before discussing the two approaches I will share with you tonight, I want to say, and I hope I'm not, am I running or it's, the pace is good? Okay, but you already know the topic, so. And a bit more about robustness per se. Because this slide is a new one. I already gave this talk and I didn't have this before. But yesterday night I thought, well, I'm talking about robustness, but there is no point in this discussion where I actually talk about it. So we could define it in many ways. And this is my own definition. It's really something I came up with. I think it's a quality of something, like an entity, that is stable. It doesn't break. It doesn't act weird too easily if the context changes. Imagine your own resilience towards stress at work or in your life. If you can keep it and you can move on, even if the situation gets messy, I think we could define that as robustness. This is what we would like to have from the model. Usually in statistics, that is my background, what you do to get that is to do some change in your estimators. Maybe you remember the trimming for the average and all this changing the weights of the model, any sort of regularization. You could find many options to make the model a more robust model. But I thought, why don't we do a different thing? I mean, it's not me. Of course, it's a field for its own. I'm just showing you some ideas from that. I'm not the owner of them. Why don't we avoid modifying the models, but we just look for the chickens and keep them away, and we prevent them to get into our systems? Why don't we just protect it instead of changing it? So in another metaphor, forgive me if it sounds silly, but in the fight or flight or freeze response, maybe someone of you heard about this physiological concept in our body, we choose to fly. So we don't fight back. Yeah, this is probably, I can remove it. But I told you I did this yesterday. So last contextual information, piece of information is that we are facing a risk. And there is an increasing attention about risks in AI. Risks that can be of many different sorts. And depending on the field you are working in. I know that someone you work in payments, and so highly sensitive and risky field, but imagine autonomous driving or healthcare. There are risks that are just unacceptable and risks that are minimal. And the most interesting thing here is that it's becoming something under the attention of regulators. Especially EU proposed really recently brand new AI regulation that could become applicable to the industry already from 2024. So tomorrow. I'm not telling you, it's you can go to this website, and if this becomes true, and this would be the first example in worldwide, so for, at least for something, Europe would be the leader and the pioneer. Every companies like the ones we're working in should go through a mandatory assessment process of risks that would work. The contrast is not ideal, but in steps. The company should check an assessment compliance regulated and formal checklist, should define the risks that are relevant for the domain, should tell how they made their models compliant to the regulation. So what is missing now is this legal framework, but it's becoming true. And robustness, or better, the lack of it, will be one of those risks. It's, again, if you go to this document, it's one of the, I don't remember, 4 or 5 kinds of risks that are already described in the, so politicians are working on this right now. So just to give you a little bit of the relevance and how urgent this is. So tonight I show 2 approaches to define a robustness matrix. One that is based on generative adversarial networks, where what we do is try to decide if making a prediction is worth the risk, checking the stability of the classifier, and we will see how. The second one is based on a variational autoencoder, and here we decide if a prediction is worth the risk, checking somehow the true origin of the input. So the focus is a bit different. There are strong connections between the 2 approaches. Let's see them quickly, or not so quickly, but now. So the first approach. In a nutshell, generative adversarial networks are kind of, I don't want to give for granted that, but I'm sure every one of you know already them, but anyway, it's a composition of 2 neural networks, where one network that is called generator takes some random noise and produces some input, like the digits. And there is another network that is the discriminator, also called critic in some literature, where that decides if the input that is coming from the generator is authentic or a made-up one, an artificial one. The idea is that if you do this many times, at some point, the generator becomes so good in doing this that the discriminator cannot distinguish anymore between the real inputs and the artificial ones. So, in a nutshell, GAN, simply 2 networks, one creates, the other decides. After some point, who decides is not able anymore to distinguish. So for this approach, we use a bit fancier GAN, the Wasserstein GAN, that simply uses a different loss function. The loss function for this is a Wasserstein distance that is a measure of the distance between probability distributions. It's really not relevant now, the exact choice of this loss function, but more details this link. What is relevant instead is that compared to the normal GAN setting where you have where you have 2 networks, now we add a third one, and we call it inverter. What does this inverter do for us? It takes the input that the generator created, like the fake digit, and translates it back to the noisy, to the latent representation of the that is the generator is using. So it's exactly, let's say, the inverse function of the generator, more or less. The overall picture of this approach is this one. So we generate some stuff, the critique or discriminator decides something, and the inverter translates back. We have a loss function, we have of the inverter, we have a loss function of the Wasserstein gun. With this framework in mind, how do we build a robustness matrix? And now I really need your attention because this is a little bit tricky to explain. I find it quite tricky. So focus on a new data point. Chicken is coming. I take the chicken, for which I have my classifier that is making a prediction. It says 6, no? I take the chicken, I translate into with the inverter, into the latent space that we learned in the way we created before. And this provides this object here. Let's call it Z first. Starting from Z first, I look around Z first, the latent representation of the chicken, and I check for the data point in that representation for which the closest data point to it that is able to confound the classifier. So if it said 6 before, now it will say 8 or 10 or 0 or 1, 10 no, or 0, 1 and so on. So I'm checking, I'm translating the chicken in the latent space, and I'm checking around this point, the closest point that is able to make the classifier change its mind. And the idea is that if I had to do really little effort to make the classifier change its mind, then maybe the classifier is not really confident about it. Do you see what I'm going, more or less? It's a, I had to repeat yesterday this many times to say it. So the robustness matrix at this point could be the following. I simply take the difference somehow of the translated chicken in the latent space, the translated chicken in the latent space and the closest point that is able to fool the classifier. And I should then be able to, as I said, if this object is really small, then the classifier was really easily fooled. If this object is really big, then it seems that our classifier, it's stable. So stability maybe here is the keyword. And of course, the big question here is, okay, how do we define if it's big or small? How do we find the threshold to define where I should make a decision and where I should make the opposite one? On this hot topic in a moment, first I want to tell you about the experiment I did, actually already some time ago, implementing this in PyTorch with a generator, a discriminator, and an inverters that are all convolutional neural networks using simply Adam for optimization. And doing after a training, what I did was to find the distribution of this delta Z, where on the test set. So the W gun didn't see these points, and I check how in a control setting, because I know test set, I know the labels, how this is this distribution look like. And they look like this box plot here. So I have this object, and what a statistician like me would do really easily, super basic, is to take the percentiles, the quantiles. And for example, I ask myself, okay, what if I take the 5th percentile of this distribution, and I check the chicken compared to this number. And I was glad to see that the delta Z for the chicken, that was a really small number, as expected, was way smaller than the threshold. So in my setting, this would mean discard the prediction. You found something weird. Do not make a prediction. or if you already made it, don't use it. And it looks like a good thing, but we have to say something more. Yeah. The classifier, the original classifier. This is a very good question. So it's a good question because it makes really different from the next approach. We check the F. The F is the original. Mm-hmm. No, it's being to so the effort that I have to make to fool the classifier for the chicken will be much smaller than the effort that I have usually to do on real digits. Yeah, the distance between the translated chicken or translated digits and this point, or this the point where I have to get to be able, the closest point where I have to get to be able to change the opinion of the classifier. Well, but it's not. We are not trying to classify there. So if you look at, if you have in mind classification boundaries, I think it's something not happening here. I'm not taking the latest space and looking for classification boundaries because I have to say 0, 1, 5, 6, 7. I take the digit as a digit per se. I don't care about the label. I just know that it's a reliable input. And whatever is the digit, this will have, of course, some impact on the actual position in the latest space where I'm in that moment, digit by digit. But the assumption, of course, it's questionable. It's an assumption for this reason, is that no matter what the digit is, as far as I have an actual digit, this effort, as I define it, will be much bigger than just random pictures. I don't know if this answers somehow, but we can go back in this during the Q&A. But yeah, sure.
It's a little more experimental. Basically, the assumption is that the mood change or generative change in the equal distribution will produce generative change in the output.
Yeah.
That's kind of an assumption that probably holds in most tasks. And again, but it's kind of an assumption of this strategy to that.
Yeah, it's an assumption that may actually, I didn't say how we look for this closest point. The searcher algorithm, it's a huge, like it's another, in this example here, the experiment that is proposed in literature is using a iterative, recursive searcher and an iterative searcher. So the way you look for this closest point is already not well defined, is ambiguous for its nature. So the assumption is that given that there is this kind of smoothness and that we have a proper searcher that is able to use it, we will find this closest point, but in a way that makes sense. That's why I don't really think this first approach is the winner of the evening, because as you can see, it's quite complex. It's already, we need a searcher, we need 3 networks, and we still need the classifier. So, but anyway, I think it's cool as approach itself. But if you are patient enough, we'll come back to all the questions in one moment. But let's say that we are fine with this distribution of delta. The point is, if I just check the the single data point, the chicken, and say, oh well, it's smaller than the threshold, I'm done. No. What you should do is to test with many chickens. In this example, the many chickens are the fashion MNIST dataset. And if you do the same with the fashion M-NIST dataset, using the same percentile, the same threshold, we find that we have a 5% of false positive rate by definition, but this means losing the almost 35% of actual good prediction. So in the 35% of the times, we are finding chickens that are not there. And this is, of course, not a good result. This is just to tell you that there is the need of tuning the threshold, and an option could be up to, and I don't say this now, the option, of course, is changing the threshold, and you will see the result in the second approach. Let's brief a moment now. So, main points here. And I think this is the coolest thing for me about deep learning. I don't know what you think about. And the idea is that it's like looking at the data from a perspective that you never had before. You get into, like, it's opening your mind. You go in this latent deep space, and you see the data really close, really magnified somehow. So the idea of using this magnification that comes from features extraction, basically, I find it very, very fascinating and powerful. So first idea, using the latent representation, finding some sort of threshold, tuning it somehow. Second approach, and I'm going to close in 15 minutes, so please keep it folded. So this second approach, I think it's easier, disclaimer. Theoretically, I don't know how how proper. Let's have a discussion about that. So first, what an autoencoder is without DB. It's simply, once again, a composition of two networks. There is an encoder that takes the input and kind of compress it. And I know that to use the term compress is wrong, so it just compressing in the latent space. And then there is a decoder that learns how to take this compression and to expand it back to the real original space. And if this worked well after many iterations of the training, blah, 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 almost we once again are not able to identify what is the original input and what is the reconstructor input. So not so different from the GAN, at least practically. No surprise that both are using generative approaches, of course. In the variational autoencoder, what we do is once again, instead of mapping to a static vector through a function, we learn to do this mapping, learning probability distributions that are taking the input and probably mapping to something and probably decoding to something else. So here we can say that we have a probabilistic encoder and a probabilistic decoder that are somehow approximation of a posterior likelihood and with some prior of some sort behind. There is a lot of theory, really interesting. I once again point to this blog, the same of before, for details. But for our goal of tonight, how do we use this approach for my problem of looking for the chickens? Well, for some reason and somehow we see that the loss function of a variational autoencoder is somehow not directly measuring the probability that an observation comes from the distribution underlying the training set. If this is true, or even if we don't say like that, but of course the loss function is telling us how hard was the decoding after the encoding. So if the encoding had happened and the decoding was perfectly perfect, we would have what would be the loss function? A 0, right? Okay, I just wanted to check. So 0 means they are the same. If it's small, almost the same. If it's big, it didn't work. So an unlikely input, like the chicken, we expect, again, an assumption, that would produce a big loss function observation, of course. We plug in the chicken in the loss function, and we get a number, no? And that's simply the robustness matrix here. As I told you, really easy. The loss function itself. I take big loss as a sign of not robustness, of a not robust prediction. And I take instead a small loss as an indication of, okay, I trust you. And the coolest thing here is that we don't need the classifier at all. The F is not
very large for itself. So once again, there is the problem of the threshold, and I need to check. In this case, the direction of the comparison is the opposite. We discover if the loss function of the unit to be length bigger than the threshold. The others, of course, the other way around. Yeah. Question. What, sorry? The learn structure. Yeah, because we do this in the process of taking the structure. But we check this to find the threshold. We do it against exactly the same experiment. We train it. Some here extremely easy architecture, not even conclusion methods, but just as an example. So can always find for a reason. I do the training, I check the loss distribution of the left side of the structure loss. And I once again check for a threshold. In this case, I want to be super sure, right? I just take the max. And they say, wait, you know what? No matter what happens here, if you are smaller than the maximum, the inclusion, the maximum that you observe, that's a start. That is super conservative, right? In this case, we by definition get a 0% false positive. That is good for the chicken. We of course didn't miss it. But what happens if we have managed? Well, with this maximum, we still have some loss addition, but way less than for the same experiment, only almost 4% of false negatives. Instead, if I scale down a bit, when I take the 90% that's loss function of the threshold, so meaning I have a 5% rate, I'll get a 0.5% of loss fields. That seems good. Of course, to be minus over 5 metrics from all the other domains. I wouldn't expect that, I didn't see that, but just to get the idea. And I'm going to go to the end. How I put this ideally, why this is good for me. I can train myself fun. And this is already fun in the end. Then I train on the same data, if that's basic professional related, I don't think so. Is on my training my introduction because what I need here is just to check some control data, the distribution of the reconstruction name. Then I get the distribution of this training variational encoder test set. I define a threshold, and here the data scientist inside us to come and forget the term. There is no, at least in this approach, it's not optimized yet. Yeah, it's the problem. So the usual what you usually name is it's a business and or a domains. And then we some kind of additional classifier where we just the definition as I said, we don't need it for meant for recording. We come to the structure of the sound, we parameters of the application, we put at least level of orientation. We check that the differential that we raise is not reliable application except say no distribution. So coming to the conclusions after all of these ideas and approaches, I think there are a few pros and cons that I see. I think you see them as well, and I hope also the other ones. I start with the pros. We don't need to modify our classifier. So the standard or old school statistical robustness goes away. Just say done. There is a resolution of this, also with learning. Take me get rid of something, what we see. So we are evolutionists, but no need to modify classifier. We can use the same monitoring system for many methods. If I have 10 models running on the same data, I can have a single checker, a single monitoring system, because the data is the same. I can apply this on every kind of data. I don't need images. Images is the easiest way to realize how this works. Why don't we use it for other things? And it's also easy to explain. Easy. But I mean, apart from technical details that are not details, but at least the general idea is, I think, very straightforward, right? And it's easy to plug in to existing pipelines here. Once again, easy is should be defined. The cons I see is that arbitrary threshold is a huge problem. There is no, and especially it's defined on all a given trainings or test set, so a realization of the distribution in the distinct life identified on the we know that because many times we would like to see different realization of correlation, so we assume stability now in the world around us. This stability is not given, should be given to rent, blah blah blah. So of course behind credit we look at many interesting details, but at the end someone has to decide. And these are points. Accountability. The final consistency is that we are introducing early one.